So, welcome again to the new lecture of the course Properties of Materials. Let us just briefly first see what we did in the last class. So, in the last class we are talking about Fermi-Dirac statistics. Which is basically probability of finding an electron in the energy space. So, essentially when you plot Fe as a function of E, if you have an energy, Fermi energy is the energy at which, Fermi energy is the energy above which all the energy levels are empty at 0 Kelvin and below which all the energy levels are filled at 0 Kelvin. So, at 0 Kelvin the plot shows this kind of nature. So, this is at 0 Kelvin and this is the EF. So, everything is, so this is the probability 1 and this is probability 0. So, at 0 Kelvin everything, every energy state up to EF is filled and all the energy states above EF are empty, and of course energy states are quantized. As you increase the temperature, increasing the temperature leads to some electrons crossing from this side. So, these are the electrons which have crossed from this side, they have gone over here. Okay. So, these two areas are equal and this is 0.5. So, basically at temperature greater than 0 Kelvin, the energy levels in the vicinity of EF, just below EF, they lose their electrons which get thermal energy. So, these are the electrons which are present here, they get excited by thermal energy. So, basically thermal energy it moves them from here to here. So, essentially this is a sort of band in which then they conduct, because some states are empty, some states are free. So, this is the band in which they conduct. So, basically now you have room for movement of electrons, and this also causes an imbalance in the velocity of electrons. If you plot the E versus K plot, so on one side the velocity is lower in the K space, on the other side the velocity is higher. So, this results in net velocity. Okay. So, this is K, this is E. So, basically you can say that there is a net velocity of electron which allows them to conduct under the influence of electric field. So, this is when electric field is not equal to 0. Okay. And then we looked at basically what happens when you apply electric field gives rise to acceleration ma, but you cannot have infinite acceleration. So, as a result A is replaced by drift velocity, which is average out velocity divided by relaxation time tau. Tau is the, so when electron travels in a lattice, so this is the lattice, let us say, and you have electron traveling. So, electron undergoes collision. Okay. So, it undergoes collision, this collision tends to decelerate the electrons. As a result, there is the average velocity of electron Vd, which is drift velocity, and tau is the relaxation time, which is the average time spent between two successive collisions. So, Vd we can define as drift velocity, or you can say averaged time averaged velocity, and tau is the relaxation time of electron, that is time so this is, we can say, average time spent between two successive collisions. So, as a result we saw that m into Vd divided by tau is equal to E. So, from this we got drift velocity is equal to E tau divided by m. So, this E is basically electric field, not the energy. Okay. And from this we calculated what is the flux of electrons. flux of electrons is nothing but, so J, let us say, is the flux of electrons, which is essentially nothing but number of electrons of charge E moving at a velocity Vd. So, if you look at this number, so if you look at this quantity, this is basically in amps per centimeter square. Now, let us see, so this N is in per centimeter cube, so this is 1 over centimeter cube, E is Coulomb, Vd is meter per second, or sorry, this is, let us say, meter cube per second, and this is ampere per meter square. So, this cancels with this, so you have, so this becomes m square from m cube. So, what we have essentially Coulomb per second per meter square, and what is Coulomb per second is the ampere. So, basically it is number of charges, total amount of charge flowing to certain length per unit time. So, that is essentially so basically it is amount of charge travelling per unit time per unit area. So, that is what it is. So, J is equal to NEVD, you can say amount of charge travelling per unit area per unit time. That is what the flux is basically. So, if you now make the substitution, we write J as NE square tau divided by m into E, and this term is nothing but sigma, that is electrical So, this is where we were yesterday. So, we defined the sigma is equal to NE square tau by m, and this is equal to 1 over rho, and this is a fundamental relation for metals or conductors. So, basically you can say conductivity, so you can write basically sigma is equal to J divided by E. So, essentially it is flux per unit potential gradient. This is what it is. Now, you can see that sigma is proportional to NE square tau divided by m. So, sigma is proportional to n, it is proportional to E square, it is proportional to tau, it is inversely proportional to 1 over m. In this, this is a constant, this is a constant because it is mass of electron, let us say me, this is E which is a constant. What varies is n and tau. So, if you can increase, so basically if n increases, sigma increases, tau increases, sigma increases. Now, n is generally something which is fixed for a given material. So, and does not change too much. So, what you can however affect for a given material is tau, and this tau is relaxation time, which is basically is a function of basically scattering. So, more the means of scattering of electron are, lesser is tau. So, essentially what we say is that if you have things in the material which make electron collide more or scatter more, so it will have less average time spent between the two collisions. So, essentially what are the things which lead to, so causes of so one is we have seen is lattice scattering, because ionic cores are vibrating. So, this is because of vibration of ionic cores, and as a result you have lattice scattering that will be present in any material. Other means could be defects, you can say dislocations for example, you can have grain boundaries, and you can have impurities. All of these things will cause scattering, and so if you increasing the amount of obstacles will increase the scattering and hence decrease tau. All right. So, this is what basically tau will be. So, and this tau is essentially related to what we say is the mean free path. Mean free path is the average distance travelled between two collisions. So, of course, when you do not have, for an ideal crystal, for an ideal material at 0 K, there are no lattice vibrations, no defects. So, which means the L should be equal to infinite or tau should be equal to infinite. So, basically conductivity should also be infinite for ideal material, but that is not the case because materials realistically have defects, some defects always present, and they also have impurities. As a result, you will always have some finite. So, basically what we are saying is that adding impurity, increasing temperature and increasing defects will increase resistivity. Okay. So, essentially if you look at the case for instance copper, let us say we make a case for copper, this is temperature axis, this is resistivity. So, let us say this is the case for pure copper, the resistivity increases, and basically whatever contribution you have at this point is basically you can say rho thermal, and rho is nothing but 1 over sigma. Now, let us say we add little bit of nickel to it. When we add little bit of nickel to it, so this is pure copper. When you add little bit of nickel to it, so let us say copper plus 10% nickel. So, when you add 10% nickel, it increases the resistivity. So, as a result, the extra contribution is rho impurity. Okay. Now, let us say you add some amount of deformation to it. So, when you add some amount of deformation to it, then this is the extra contribution that you create as a result of rho defects, because deformation causes dislocations and defects to be created, as a result resistivity. So, this you can say is copper plus 10% nickel plus deformation. So, deformation causes defects and defects. So, that is how the resistivity will vary. So, essentially resistivity increases with increasing impurity content, increasing temperature as well as increasing defect content. So, basically we can write this rho as rho thermal, which is the basic component, plus rho impurity plus rho defect, and where rho thermal is approximated as rho naught plus alpha T, and rho impurity is given as A some constant into Ci, which is the impurity concentration, into 1 minus Ci. And basically this you can say is additive kind of rule. So, this is basically you can say is Mathiasson rule of addition. Okay. So, I would suggest you to go through a few examples. So, what you do is that you take different values of n, different values of E, different values of tau, and try to calculate, sorry, you can take different value of E, but only different value of n and tau, to see what are the different conductivity values you can calculate from and this will also be part of assignments that will be given to you. Okay, so now what we have said is, we have first talked about the conductivity of metals. So conductivity of metals is sigma is equal to Ne square tau over m, which is a reciprocal of resistivity, and conductivity decreases or resistivity increases with increasing temperature, increasing impurity concentration and increasing the defect concentration. So this is what it is about the metals. Now what we do is that we so let's just work out certain numbers for just look at the table for certain materials. So let's say comparison of a few metals at room temperature. So let's say, let's make a list: silver, copper, gold, aluminum. We can also add tungsten because it's an important thing. So let's see, and we can have canthal. Canthal is basically molybdenum disilicide, which is used for heating filament. So resistivity into 10 to the power minus 8 of ohm meter. Okay. So if you write for silver, it's about 1.5, for copper it's about 1.7, for gold it's about 2.2, and then aluminum it's about 2.8, for tungsten it's about 5.5, and for canthal it's about 135. So these are certain resistivity values, and you can also write things like what is the temperature coefficient, alpha, which is nothing but Kelvin inverse. Then we can write density, and we can also write tensile strength, which is MPa. Okay. So for silver it's 0.004, for 10.49 density, which is gram per cc, and then it is 125 MPa. And if you look at copper, it's 0.0043, this is 8.96, and this is 210. Gold is 0.0035, this is 19.32, gold is very heavy, and 138 is the tensile strength. For aluminum it's 0.0042, this value is 2.7, and this is 60 MPa, very weak. Tungsten on the other hand, which is used in bulbs, it has a coefficient thermal expansion of 0.0045, and then 19.3 is the density, but its tensile strength is extremely high. That is why we don't use gold, we use tungsten for making the. So this is temperature coefficient of resistance, not coefficient thermal expansion, by the way. Okay, so you can define this as alpha is equal to 1 over r into dr over dt. This is alpha, and the value for canthal is 0.00003, and this is 7.2, and this is 800. That is why canthal is generally used in furnaces where you don't want very high coefficient where you want high strength as well as high resistivity for heating. Okay, and basically the resistance of these tungsten and canthal is essentially useful for resistive heating. Because of I square r term, so higher the resistance is because of I square r losses, and that is why if you have copper and aluminum, they will not lead to too many losses, but if you have things like tungsten and canthal, that will lead to and you can manipulate the resistance also by changing the can be manipulated by changing length and cross sectional area. Okay, so essentially for transmission lines, for example, for power transmission we use either aluminum or copper because of their fabricability and mechanical strength and low Ia square R losses. And for heating elements, which should not melt easily, we use tungsten as well as canthal. So these are used in bulbs, for example, these are used in furnaces. Okay. So essentially these are the and of course other things are for heating elements we used to use good oxidation resistance and high temperature strength and so on and so forth. So this is about metals, basically basic properties of metals, that metals have the important thing that you consider about metals is resistivity and conductivity, and so which is conductivity is given as NE square tau by m. So you can manipulate the conductivity of these materials by changing n and tau, and it is tau which basically makes a lot of difference to the conductivity of these materials. Now what we are going to do is that we are now going to discuss what we say is the properties of semiconductors. Now earlier we said that Fermi-Dirac statistics says that at 0 Kelvin, so Fe versus E, at 0 Kelvin you have this kind of step function. So sorry, 1 and 0, not other way around, 1 and 0. So at 0 Kelvin all the energy levels are filled and all the energy levels are empty above EF. As you increase the temperature, the Fermi level, the curve becomes asymptotic around 0, around EF around 0.5 value, and then the electrons leave the lower part to upper part. What we are looking at metals is basically you can say metals have continuous bands. Semiconductor on the other hand is different. So if you look at these quantized state of energy, so in quantized states of energy you have bands like these, okay. At some point you will have EF, okay. So you will have EF, but so of course you have quantized bands, but the bands are, there is no large gap, okay. These gaps are smaller, as a result electron can get energy and then it can move around in those energy levels. In semiconductors what happens is that, so you can say in metals no gap, no large gap exists between energy levels. Now in semiconductors, for quantum mechanical reasons and diffraction by the lattice at reciprocal lattice points, there is a creation of gap. So essentially when you plot this EK diagram, so EK diagram is something like this, okay. This is E, this is K. Now this is K space. So K space basically will have now reciprocal lattice points will be plus pi by A, 2 pi by A, 3 pi by A, minus pi by A, minus 2 pi by A, and minus 3 pi by A, okay. What happens in EK diagram is, because of diffraction by the lattice, there is a gap created at this stage. So there is a gap, so this curve tends to become like this around this point. Okay. So basically what you have to, so a lot of these gaps are created, but you have, for a 3D solid you have a lot of energy states. So you may have a situation like for a 3D solid, when you make the band structure for a given 3D solid, it may be slightly different. For a 3D solid it may, let me show you the picture. So you may have energy levels going like this. So you will have to calculate the band structure, but what you can see here is, if you have energy state linkages, which means this is E, this is K space, you can see that in this energy space there is a gap here, but then electron can move to different K space, it can always find energy state. So there is no continuous gap across the K space for electrons to travel. So as a result, electrons can flip flop their way around the K space to higher energy state. Now supposing instead of this, what happened was that there was a clear gap. So you can see that there is a gap like this. So there are gaps here, there are gaps here, there are gaps here. So whatever the minimum gap is, so this is the minimum gap. So maxima and minima of upper and lower part. So maxima and minima of lower and upper part, this is basically what we say is the forbidden gap, and this happens because of diffraction of electrons at the reciprocal lattice points. So if this happens, then this leads to creation of energy gap, and this energy gap is basically forbidden energy gap. So you may have situation like this in semiconductors. The situation is something like this. In case of metals, so when you plot metals will have, let's say you are plotting energy states. So you will have these energy states like these. Electrons are sitting here, and then you have another maybe little gap somewhere here. Okay, and so this is, but at the same time in K space somewhere in parallel you will have these empty states. So these are all empty bands. So these are all filled bands, you can say, and this is empty band, and this is energy. So at the same energy state there are some empty states, so there is a room for electron to move. So as a result, electron can flip flop here and there, and this is what metal is. Metal has no empty energy state. In the semiconductor the situation is different. We are running out of time now, so what we are going to do is that we will discuss that in the next class. So in this class basically what we have discussed is, we have discussed about the little bit details of how the conductivity of metals can be varied by changing impurity concentration, by causing deformation, or by increasing the temperature, and then we move to semiconductors. We just started talking about creation of energy gap, but we will discuss this in more detail in the next lecture. Thank you.